Hello, I'm going to do another video, a follow-up video to the two videos that I already posted, and it's going to be in response to some comments that Ed McMorrow made and also James Kessler. I'm going to look at C4 instead of the C2 this time. And I'm going to look at the effect of hammer hardness, because James Kessler asked the question, would it make any difference in terms of the sound of the wave, the bridge force wave, if it was a higher frequency key? And it turns out it does make a slight difference. It's hard to perceive, but it got me thinking, because the real parameter to vary here is not so much the stiffness, but it's the hardness of the hammer. So I'm going to start out with, on the first string, it's going to be a hard hammer. 2.5 is hard. That's the exponent in that expression for generating the force when the felt is compressed. And for the second one, I'm going to go with 2.8, which is a softer hammer. And we'll see what the difference is. Okay, here is the same plot I had before. Difference is, here's the plotting along the string. The string is shorter because it's a shorter string key, C4, so it's a little over 6.6 meters. Still striking here at the green spot. So I'm plotting against position, the amplitude. Over here I'm plotting the bridge force exchange, or the force exchange between the bridge and the string at the bridge, and I'm plotting it versus time. So here's the force along this axis, and here's the time. Okay, let's let it rip. Okay, we start off, and right away you see that the number one string, which is the one that has the hard hammer, is coming up more strongly than the softer hammer, which would be expected. Okay, and it looks like the harder hammer is moving along a little bit ahead. Here's the bridge force, quite a bit different. Blue is the first string, has the hard hammer. Red's the soft hammer. And they both have stiffness, because that stiffness parameter is the same for both the hard and the soft string. Okay, I'll let this thing run its usual length of about a period or so. Okay, it stopped at 9.5 milliseconds. You see, that's a lot shorter than the other videos which dealt with C2, but it should, because it's a shorter fundamental period. This thing is about, what, looks like about 2.2 milliseconds here, and it's about 6 here. It's about a little less than 4 milliseconds. So that makes sense, because you take 1,000 and you divide it by the 261, which is about the fundamental period, frequency of C4, and you get 3.8, which is about the distance between these two peaks. So it repeats every 3.8 or so milliseconds. And here is the force exchange between the bridge over about, well, 1, 2, 3, 4, 5, 6, almost 7 cycles. And you can see the hard hammer generates more force, higher peak, and also shows the ripple. The soft hammer has a lower peak, and it's much smoother. It doesn't really, well, there's a little bit of difference. I'd say probably, if you compare this rise point here on red with this rise point here. It's a little bit different, but not much. So the softer the hammer, the less impact you have from your dispersion. Here's the spectrum. Let's look at the longer one. Yeah. Okay, so now we have both exhibit similar amount of dispersion or inharmonicity, but the peaks are a lot lower. There's a lot more power for the soft hammer, the red, in the lower frequency than in the higher. And I calculated the spectral centroid, or it's the tone center for these two. And the tone center is basically the frequency about which the tone power is centered. So if you have a lot of power in the high frequencies, your tone center is going to be high, and vice versa. So for that hard hammer, I have a tone center of 370 hertz. For the soft hammer, I have a tone center of 280, basically 290 hertz. So now, let's listen. First, the hard hammer. Okay, that was C4. Now the soft hammer. And I think you can discern the difference. Okay, thanks for watching and listening.